Hey, welcome back. All right, today we're going back to basics, breaking down the very stuff that makes up our world, solids, liquids, and gases. And we're going to use some classic science puzzles to guide us and get to the heart of how this all really works. Ready? Let's dive in.
Okay, right off the bat, I've got a little puzzle for you. Imagine we've got three identical syringes, and each one is filled with a different state of matter. We push the pistons. Now, just by looking at how far those pistons have gone down, can you tell which one has the solid, which has the liquid, and which has the gas? Figuring this out is the key to understanding one of the biggest differences between them.
So how do we solve that syringe puzzle? Well, the trick is to think small, like really small. We've got to zoom all the way down to the particle level. Everything, and I mean everything, comes down to how these tiny invisible particles are behaving.
And here's the answer. The magic word here is compressibility. Look at syringe C, where the piston moves super easily. That one, well, that has to be the gas, right? Because its particles are super far apart, with tons of empty space you can easily squeeze. And syringe A, where the piston barely budged, that's our solid. Those particles are jammed in there, tight as can be. That leaves syringe B, with just a little bit of movement, as our liquid. So what's the big takeaway here? It's the space between the particles that dictates how much you can compress something. Okay, let's expand on that idea a little. This table lays it all out. Take a solid, like wood. The forces holding its particles together are super strong, which is why it has a definite shape and volume. Now look at a gas, like helium. The forces are incredibly weak. The particles are just zipping all over the place, which is why a gas will fill up any container you put it in. And liquids? They're kind of the cool middle child. The attraction is strong enough to keep a set volume, but not so strong that the particles can't slide around and take the shape of the container.
So, let's just nail this down. Solids, they hold their shape, they hold their volume. Done. Liquids, they'll take the shape of the container, but their volume stays the same. And gases, man, they're the wild ones. They take the shape and the volume of whatever you put them in. It all just boils down to how much freedom those little particles have. Okay, but here's where things get really interesting. You see, these states, solid, liquid, gas, they're not set in stone. If you add or take away energy, usually in the form of heat, you can actually force them to change, to transform. This is where we get into phase changes, and temperature is the name of the game.
So that brings up a really practical question, right? I mean, you just know that water is a liquid at room temperature, and a chunk of wood is a solid, but why? How could you figure out the state of some substance you've never even heard of? Well, the answer is all about two magic numbers, the melting point and the boiling point. The melting point is the temperature where a solid flips into a liquid. The boiling point is where that liquid turns into a gas. You can almost think of them like boundary lines that tell you exactly what state something's going to be in.
All right, let's put this to the test. We'll use room temperature, which is roughly 25 degrees Celsius. So for substance P, its melting point is 20 and its boiling point is 115. Where does 25 degrees fall? Right in between. So it's a liquid. Same deal for Q. 25 degrees is neatly between negative 46 and 59. Another liquid. But now look at R. Its melting point is way up at 107 degrees. Our 25 degrees is way below that. So what does that mean? It's still frozen solid.
And that's it. That's the one rule you really need to remember. If your temperature is below the melting point, it's a solid. Above the boiling point, it's a gas. And if you're right in that sweet spot in the middle, bingo, you've got a liquid.
All right, so we get that temperature is the trigger for these changes. But what does that process actually look like if we could watch it happen? Well, we can. We can map it out on a graph. And these graphs, these energy curves, they tell a really cool, hidden story about what's happening with all that heat. Okay, but before we look at the graph, we've got to wrap our heads around this kind of weird idea called latent heat. So get this, when something is in the middle of melting, or boiling, you can pump more and more heat into it, but the thermometer won't move. The temperature stays totally flat. So where's all that energy going? Is it just disappearing? No. It becomes this hidden energy. That's what latent means. And its whole job is to break the bonds holding the particles together, not to make them move faster. And this graph right here, it shows that idea perfectly. This is a heating curve. You've got temperature going up the side and time along the bottom. So what's the story this graph is trying to tell us about substance P? Let's walk through it, step by step. Okay, from point I to I2, things are simple. We're heating up the solid, its temperature is rising, particles are vibrating faster. Easy enough. But then look at what happens from I to 3.
We hit that first flat part, the plateau. That's the melting point. The temperature stops rising because all that heat energy is being used as latent heat to turn the solid into a liquid. Then, once everything's melted, from I to 4, the temperature of the liquid starts to climb again. And then boom, another plateau from I to V. You guessed it, that's the boiling point. More latent heat is being absorbed to turn that liquid into a gas.
You know what's really cool is that this graph tells us even more. It gives us clues about something like density. Think about it. In that first phase, I to 2, the particles are packed in tight as a solid. But in the liquid phase, 3 to 4, they've broken free and are sliding around. They've spread out a bit. And what does that mean? It means for most things, the liquid form is actually less dense than the solid form. Pretty neat, huh?
So that's what happens when we add heat. But that's only half the story, right? What happens when we do the opposite? When we start cooling things down? Well, that brings us to the cooling curve, which is pretty much the whole process in reverse. Yeah, they're basically mirror images of each other. On a heating curve, energy is being absorbed, and you see those plateaus at the melting and boiling points. On a cooling curve, energy is being released, and the plateaus happen at the condensation and freezing points. It's the same idea, just backwards. So when you look at this cooling curve, that flat section you see at temperature T1, that's the freezing point. And just like with melting, the temperature doesn't drop while it's freezing. It holds steady while the substance releases that latent heat, letting all those particles lock back into their solid structure.
Okay, for our last section, let's touch on a couple of other really cool ways particles behave, like how they can mix all by themselves, and how sometimes they just skip a state altogether.
And that brings us to this idea, dry ice. You've seen it, right? It's that smoky stuff. That's a perfect example of something called sublimation. See, dry ice is just solid carbon dioxide, and it never melts into a puddle. It just goes straight from being a solid block into a gas. And that's sublimation, the direct jump from solid to gas.
All right, another big idea is diffusion. This is something you experience all the time. It's why you can smell coffee brewing or popcorn popping from the other side of the house. Those little scent particles are always moving around randomly, and they naturally spread out from where there's a lot of them to where there's not so many, until they're all mixed up. No stirring required. So a good question is, how fast does this happen? Well, it mostly depends on how heavy the particles are. Lighter particles move and diffuse faster. But here's a fun little brain teaser. What if you have two different gases whose particles have the exact same mass? Like, take nitric oxide and ethane. Turns out, they both have a molecular mass of exactly 30 atomic mass units. So what does that mean? It means under the same conditions, they'll diffuse at the exact same speed. Pretty logical when you think about it.
And all this brings us to the grand finale, the 6 ways matter can change from one state to another. You've got the ones we all know, melting and freezing, that's one pair, vaporization and condensation, that's the second. And then you have those special direct jumps we talked about, sublimation, which is solid to gas, and its opposite, deposition, which is when a gas turns straight into a solid. That's how you get frost on a cold window.
So there you have it. We've gone through the classic states of matter you see every day. But it kind of makes you wonder, right? We've talked about heat and pressure. So what happens when you have extreme pressure and extreme temperature? Like, what's going on inside a star or at the edge of a black hole? The rules we talked about today are just the beginning. It's a pretty good reminder that no matter how much we learn, there's always something more to discover. Thanks for diving into this with me today.